Today we'll solve some more problems of diode circuits from analog electronics. Now if you see the question, consider the circuit shown below. Find the output voltage V0 for the input voltage 5 volts. Assume the voltage drop across the conducting diode is 0.7 volts. So in the given circuit he is giving input voltage as 5 volts. Okay. Now he has given two diodes, diode D1 and D2. If you observe carefully in these diode circuit problems, we have to first look at the diode P type, which is connected to what voltage it is connected, and N type to which voltage. If you observe carefully, for the diode D1, P type is connected to 10 volts, N type is connected to 5 volts. So the potential across the diode is very high, 5 volts. Similarly, for the D2 diode, if you observe, P type is connected to 5 volts, N type is indirectly connected to 10 volts. Here, N type is coming to 10 volts. So this is almost like a reverse bias. So there is a chances for D1 to be on state and D2 to be off state are very high. Now let us consider this assumption only. With this assumption, if you redraw the circuit, 2 kilo ohms and diode D1, which is assumed to be on state. So we'll replace this diode with zero point 0.7 drop voltage. The voltage drop across the diode is 0.7 voltage. 0.7 volts. This is D1. 2 kilo ohms and 10 volts. And here it is given as 5 volts. Input is given as 5 volts. Now diode D2 is assumed to be off state. So I am considering this as open switch. And this is 5 volt here. Now what will be the output voltage? So the current flows from 10 volts through the diode D1 like this. Okay, current flows in this direction. This is diode D1. Now by applying KVL, by applying Kirchhoff voltage law, you can write the equation 10 volts minus 2 into 10 to the power of 3 multiplied by current I minus 0.7 volts minus 2 into 10 to the power of 3 into I minus 5 volt is equal to 0. So now by solving this equation, you will get I as 1.075 amperes. So what is the output voltage now? Output voltage is equals to 10 volt minus 2 into 10 to the power of 3 multiplied by current I. Because output voltage is coming here, we have to subtract the voltage drop across this 2 kilo ohms from 10 volts. Then only output voltage will be there. So what is I here? Here the current I is 1.075 amperes, which is equals to 7.85 volts. So now the answer is option C. Now let's see one more question. The circuit shown in the figure is, this we have already seen and already discussed in the previous videos also. This is a clapper circuit. Okay, this is nothing but a clapper circuit. Whenever a capacitor and diode are involved, it should be a clapper circuit. And if two diodes and two capacitors are involved, it must be a voltage doubler. Okay. Now if you see here, V out, input voltage is a sinusoidal waveform. That is input voltage here. So during the positive half cycle, the diode does not conduct. During the negative half cycle, diode conducts. And current flows in this direction, charging the capacitor to plus Vm voltage. So from then onwards, output voltage will be Vm, the voltage across the capacitor, plus Vin, input voltage. So it is shifting the DC bias of the input voltage to the positive way, positive DC. This is the input voltage. This is the input voltage with the positive peak as Vm, negative peak as minus Vm. This is being shifted. This is being shifted like this. The sinusoidal waveform is shifted with bias voltage as plus Vm. So the output will be like this. So this is adding a DC signal, DC shift to the input voltage. That's why it is a clamper. So it is a positive clamper or a negative clamper. Now this is acting as a positive clamper because it is shifting the sinusoidal waveform to positive side. Now let's see one more question. What type of diode circuit is used to add or restore the DC level to the electric signal? The answer is clamper. Okay. The above given figure is a positive clamper. Then what is the circuit for below for a negative clamper? This is the circuit for negative clamper. There is a capacitor C. Just simply you reverse the direction of diode. This is the circuit for negative clamper. This is output voltage V0. This is input voltage V. Here during the positive cycle, positive half cycle, the diode converts and the capacitor C charges to Vm voltage. Okay, but if you look from output voltage side, the output voltage is equals to minus Vm, the voltage across the capacitor, plus Vb. So it is shifting the sinusoidal voltage, sinusoidal input voltage bias to negative side. This is the input voltage with zero bias. It is being shifted like this. This is 0 volts and this is negative Vm minus Vm. So the output will be like this. It is shifted to the negative side. That's why this is negative clamper. Okay. If the diode is facing downwards, it is negative clamper. If the diode is facing upwards, it is a positive clamper. Now we'll see next question. Which type of diode is used to clip off the portions of signals above and below certain levels? It is clipper circuit. Okay. Now let's discuss the clipper circuit. First, we'll discuss negative clipper. Clipper circuits vary. There are three types. Okay, this is the input voltage. This is the diode circuit, and this is the resistor. Alright. If the input voltage is sinusoidal voltage, the input voltage is a sinusoidal voltage, the output will be positive waveform only. Only positive cycles will come. Negative half cycles will be clipped. Why? Because during the negative half cycle, diode conducts. During the negative half cycle, diode conducts, and output will be approximately 0 volts. So this is a negative clipper. Similarly, for this negative clipper, to this negative clipper, if you add a bias voltage, assume you have taken, this is the negative clipper diode, you have added a positive bias voltage, VR. Assume this is VR. Then what will be the output voltage? Here, for the input voltage, sinusoidal waveform will be like this. It is usually the negative clipper is supposed to produce only positive half cycles, like here. But here what happens in this case, as you have added a positive bias, the positive portion of certain level will be clipped off. Positive level, the positive portion in the positive half cycle of certain level, that is VR level, will be clipped off and output will be like this. Output will be like this. Okay. So up to VR, it will be clipped off. This portion is clipped off because you have added a bias. So output will be like this. Similarly, for the same negative clipper, if you add a negative bias voltage, why I'm saying all these things, why I'm teaching all these things is, by looking at the circuit, you should be able to judge what is the output waveform in the examination. This will save your time as well as efforts. You have to practice this. The input voltage will be like this. In this case, the input voltage is a sinusoidal waveform again. But here you have added a negative bias. So what happens is, it will save some of the portion of negative voltage. So now the bias is shifted to minus VR. This is VR. So now the output voltage will be like this. Positive half cycle plus some portion of negative half cycle also will be there. Positive half cycle, some portion of the negative half cycle. The output goes like this. So by just observing the diagram, you should be able to judge what is the output waveform. This is about the negative clipper. Similarly, for the positive clipper, if you see, we'll see the positive clipper also. The diagram for the positive clipper will be like this. This is the input voltage. Diode is faced downwards, and there is a resistor. Ah. So during the positive half cycle, diode conducts, so there will not be any output during the positive half cycle. This is the input voltage and output voltage. During the positive half cycle, the diode conducts, so output voltage will be 0. So negative half cycle will remain like that. This is ideally the output voltage of positive clipper. Now, similarly, if you consider the positive clipper with the positive bias voltage, diode T, and a positive bias voltage plus VR is applied, what will be the output waveform? The output waveform now contains negative half cycle plus some portion of the positive half cycle also. This is the input voltage and output voltage. Here the bias is shifted to plus VR. So it contains negative half cycle as well as some portions of positive half cycle also till VR. So output will be like this. Okay, by just looking at the circuit diagram, you should be able to judge the output voltage. Now, similarly, for the positive clipper, if you apply a negative bias voltage minus VR, the output waveform contains the clipped negative half cycle, the clipped form of negative half cycle. This is the input voltage. The output voltage reference has now changed to minus VR. So it will be like this, clipped form of negative half cycle. Sorry. Clipped form of negative half cycles. So hope you understood how the input voltage and output voltage waveforms will be for positive clipper, positive biased clippers, negative clipper, and negative biased clippers. Okay. Now let's see one more question. The diodes used in series to increase the current carrying capacity, increase the PIV, reduce the PIV, reduce resistance. Now let's see PIV. We have already seen it's the maximum reverse voltage a diode can withstand. A diode can withstand. Now let's see a circuit. I have a diode whose PIV voltage is 20 volts. Means the diode is manufactured with the peak inverse voltage of 20 volts. I have applied a reverse voltage of 20 volts. So if I increase this voltage, diode gets damaged. Okay. So in this circuit, I must use a diode with the minimum 20 volts PIV rating. But I have only two diodes. Assume I have two diodes, diode D1 and D2, whose PIV rating is 10 volt. Then what to do? Then what you can do is you can connect these diodes in series. You can connect these diodes in series and apply to the voltage in the circuit. So now this 20 volts reverse voltage will be dropped as 10 volts across D1 and 10 volts across D2. So now the benefit of using the diodes in series is you can reduce the PIV rating of the diodes. Rating of diodes. That is the advantage. So answer is option C. We'll see the next question. In Zener diode, only P type is heavily doped, only N type is heavily doped, both P and N regions are heavily doped, both P and N regions are lightly doped. See, Zener diode is a special purpose diode in which both regions are heavily doped. P and N regions both are heavily doped in Zener diode. Now let's see one more question. The peak-to-peak ripple voltage for a half-wave rectifier circuit operating at 60 Hz has a 680 microfarad reservoir capacitor. An output voltage of 28 volts and 200 ohms load resistance will be nearly. So here in the circuit is asking for half-wave rectifier. So for the half-wave rectifier, when the capacitor is connected at the output, it will produce a rectified and a filtered output. Now we draw the circuit like this. This is a diode D1 and the output of which is connected to capacitor whose value is 680 microfarads. So the diode basically indicates it is a rectifier. Capacitor and a resistor basically indicate that is a filter. RL is equal to 200 ohms. So it is nothing but a simple half-wave rectifier with a capacitor filter. So here V naught is the output voltage. So the given parameters are RL is equals to 200 ohms and frequency is given as 60 Hz. 60 Hz is the input voltage frequency. And DC voltage, average DC voltage at the output is 28 volts. Now the peak-to-peak ripple voltage. He is asking the peak-to-peak ripple voltage. The ripple voltage formula for a half-wave rectifier with capacitor input filter is IDC divided by FC, which can also be written as VDC, that is output DC voltage, F dot C dot R, load resistance. Substituting these values, you have 28 volts divided by 60 Hertz, 680 microfarads multiplied by 200 ohms load resistance. So here the VR comes as 3.43 volts. Okay, so the answer is option B. For those who have doubt that how this ripple voltage is equals to IDC by FC has come, we'll see the derivation here. See, basically, this is the output waveform of a half-wave rectifier. Okay, this is output waveform of a half-wave rectifier. Now, when it is connected to capacitor, the capacitor charges like this. The capacitor charges in this way. Capacitor charges to the peak value and then discharges. Capacitor charges to the peak value and then discharges. This is the way how the capacitor filter works. Now, here the time taken. Here the charging time is this. This is the charging time, and this is the discharging time. If you see the charging time and discharging time is almost greater than charging time. Discharging time plus charging time is equals to total time period, but discharging time is greater than charging time. So discharging time can be approximated to total time period. Now, whatever the amount during the discharge time, whatever the amount of charge that is stored in the capacitor is lost. E is equals to IDC, average current, multiplied by capital T. Okay, this capital T can also be written as frequency 1 by F. Now, if you relate this, the ripple voltage VR, ripple voltage can be given as delta Q by C, because this is standard formula. Q is equals to C. V is the standard formula that we have from network theory. From this, if you see, the ripple voltage is nothing but the change in the charge in the capacitor per capacitor. So the ripple voltage is equals to delta Q is nothing but IDC divided by FC, which can also be equal to VDC divided by F dot C dot R. This is the derivation of this formula. Sri Raghava Academy, online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.